Hello everyone, my name is Vladimir. I'm a final year PhD student at the TUM Munich. Today I'd like to present Rubberband, a middleware that enables elastic federated learning with help of temporary state management. Federated learning is a kind of distributed learning. The training phase in the federated learning applications is done on the user devices such as smartphones. With that, it supports the user data privacy by design. Here's a diagram clarifying how federated learning works. A pre-trained base model resides in the cloud. The model is propagated to the edge, closer to the data producers. In most use cases, edge is represented with the low-capacity aggregating nodes. These nodes derive the learning plan and provide the model to the end nodes for training. The end nodes then compute the gradients and push them to the aggregators to update the model jointly. Federated learning scenarios exhibit a number of challenges. Here's a subset. First, applications, especially in computer vision, may produce high volume of data at high velocity. NVIDIA optimistically estimates that an autonomous car produces 1 terabyte of data per hour. Second, end nodes may be moving, like cars or drones. This means frequent changes in their association with the aggregator nodes and thus load imbalances. Third, in real setting, the communication technologies and the coverage are likely to be uneven. Low bandwidth networks and unpredictable link speeds may severely impact the aggregation speed and the model consistency. Rubberband aims to address these challenges. Rubberband is a middleware that aims to enable elasticity for federated learning applications. It does so by managing the temporary state of the learning process, that is, the gradients in the deep model, and by adapting the model update process to the application requirements. At a high level, aggregating nodes in Rubberband form token rings since it is the most natural structure to ensure consistent model updates. The configuration of a ring is supported by the local register cluster. Rings are connected with each other with several shared aggregating nodes. And an aggregating node hosts a Rubberband aggregator service running in the background. It listens for the model updates. Gradient Consumer API determines how the gradients are integrated in the application and sets the policies to adapt the model update process. The gradients and the model are stored in a local storage. The design of Rubberband is based on 3 key principles. First, deep models and the gradients are the first-class system resources. Second, the aggregation is distributed and is done in a peer-to-peer fashion. This allows us to lift the resource limit of a single aggregator node. Third, Rubberband employs different kinds of state management policies to optimize for various goals like low latency or desired accuracy. I would like to support this last design point with an example. In this experiment, we evaluated whether the linear scaling of the whole model gradient size is sufficient in a federated learning setting. We did so with a simulation. The simulation ran on TensorFlow and used 7 neural networks. The data used for the simulation is an ImageNet version 2 dataset. In this result plot, the x-axis is the number of end nodes producing the gradients. The y-axis is the log scale size of gradients in megabytes. The horizontal lines represent the main memory size for several low-capacity edge nodes. For each count of end nodes, we have 7 vertical bars, each corresponding to one of the models. Here we see that already with 16 end nodes, 3 models won't fit into the main memory of Raspberry Pi 3. Then it gets worse. Another model joins at 32 end nodes. Then at 64 nodes, one of the nets optimized for the mobile devices crosses the 1 gigabyte threshold. Lastly, at 128 nodes, we observe that most low-capacity devices are insufficient to aggregate the model updates. This supports the conclusion that the whole model gradients are bad candidates to use in the edge networks where the devices have small memory capacity. Luckily, we can address this issue with a different gradient representation policy. The key idea of this policy is to send the per layer gradient instead of a single gradient for the whole model. This reduces the memory pressure but impacts the accuracy and the timely availability of the model. As the familiar plot shows, with this policy, the gradients can fit into the main memory even of a Raspberry Pi 3 for up to 128 end nodes. Lower memory pressure offered by this policy is especially useful for elastic federated learning applications in low bandwidth communication networks. Instead of conclusion, I would like to raise several discussion points that we welcome your feedback on. First, what other parts of the federated learning pipeline we might have overlooked and that should be supported? Second, what would be the best way to integrate Rubberband into the federated learning application development workflow? Third, how to better distribute and run Rubberband? And fourth, which assumptions about the application can we employ when automating the policies composition? With that, I conclude my presentation. Thank you for your attention. I invite you to ask questions and provide the feedback. Otherwise, feel free to reach out to me using these contacts. Thank you a lot for your time.